Hello, and welcome to the lecture on angular variables. And this begins chapter 10, which is all about rotational dynamics. So we're going to introduce a lot of ideas about systems that rotate about a fixed point. And in the next chapter, in chapter 11, we're actually going to do more with that same idea. Okay? All right, so this is the beginning of a two-chapter arc of many ideas involving momentum and energy and Newton's laws, but all about rotation. All right? In other words, this is the beginning of a lot, okay? And so we need to lay the groundwork of a lot of ideas. Now, luckily, your book has done a very good job of incrementally introducing rotation. We saw rotation way back in an early chapter on two-dimensional motion. We had circular motion. That's where we first defined things like period and the idea of translational or tangential and radial accelerations. Since then, we had a whole chapter where we actually did talk about non-uniform circular motion, cars going around turns, and including the forces in non-uniform circular motion. So luckily we've seen this stuff. We've had an opportunity to reinforce it. So hopefully that will make this transition easier than it would be otherwise. Okay, so let's get into angular variables. Okay, so some of this is review from those previous times we've seen rotational ideas. Good. Okay, so key terms: translation versus rotation versus tangential versus radial. What do those things mean? Okay, well, translation motion is along a line describing the x and y. Okay, so when we talk about a car going around a turn and we talk about the components of its motion, like its tangential and radial components, those are absolutely translational terms. Okay. So that's always been our approach at this. We've talked about circular motion, but always zooming in on the translation. On the other hand, rotation is motion in a circle described in radians. We have not actually described circular motion in radians before. In other words, we've focused on the idea of going around the arc rather than the arc itself. Okay? And tangential is an axis/direction that is parallel to velocity and perpendicular to the radius. On the other hand, radial is an axis/direction that is parallel to the radius. Okay? And these are both components of translational variables. Okay? Which are totally different than rotational variables. All right, let's look at a circle here. All right, so I don't know what happened. There we go. Okay, so the idea is we have a point. It's going around the circle, right, denoted here by our green arrows, right? So it's going to be taking a circular path. This is a translational acceleration. This is the initial translational acceleration. This disk is speeding up, however. So what's that? That's non-uniform circular motion. Okay, something we've seen before, but we're going to take a different, circular motion, a different point of view this time. Okay, so there we have it. All right, so notice here's the radius. The radius is defined. We also have the positive directions of x and y, some origin set at the middle, and we're also defining the direction of positive theta. That's the radians, okay? And we always want to use radians, not degrees, when we talk about angular motion, especially the kinematics and dynamics of angular motion, okay? We'll still talk about, particular fixed angles in degrees, so we got to go back and forth. But here this is a angular displacement in radians with the positive direction being counterclockwise, as seen. Okay? Okay. All right. We'll see why that's important. Okay. So zooming in a bit more, considering more information, right? So the initial translational acceleration is entirely tangential. That's a component of the translation. All right. And here we have the translational velocity at point 1 as opposed to at point 0. At point 0, the system started from rest. We're assuming that the disk starts from rest at t equals 0 and then continues to speed up from that moment onwards. This is starting and then speeding up. Okay, there's our t equals 0 and our t equals 1. Doesn't matter what the units are. Okay, as the disk has sped up, we note that the total translational acceleration now has a radial and a tangential component. Okay, we know why that is. We know because it's speeding up, so it's got to have a tangential component, and as a radial component because this is the centripetal component, and the centripetal component always exists as long as you're turning in a circle. Because if you're changing the direction of your velocity, you need to have an acceleration to account for that turn. Okay? So these are the two components of translational acceleration, right? Not components of x and y, but components of the axes radial and tangential. Okay. Again, we've seen that all before. This is all translational stuff. Here's the new bit. omega and alpha. What the heck are omega and alpha? Well, omega is angular velocity. Alpha is angular acceleration. We'll talk more about them in a minute, but their names are angular velocity and angular acceleration. In the case of this disk, it has a non-zero angular acceleration because it's speeding up. All right? And then the angular acceleration is not zero at point 1, neither is the angular velocity 0 at point 1. In fact, the angular velocity can't be 0 because the translational velocity isn't 0. If it's moving both in terms of angular motion and in terms of translational motion. All right? However, it did start from rest, and if it started from rest, if its translational velocity was 0, then its rotational velocity was also 0. Okay? And angular velocity, rotational velocity, two names for the same thing. Okay? And notice here, it says angular velocity for the disk as a whole, because that's the thing. Notice that the translational terms, whether they're velocities or accelerations, all refer to this little pink dot because they describe the motion of a particular point on our rotating disk. But the angular velocity and the angular acceleration describe the disk as a whole because they don't have meters per second in them. They just have radians per second and radians per second squared. So they don't have an x and y. Thus, they can describe the disk as a whole. All right? And here we point out that even though the system started from rest with no initial velocity, both translationally and rotationally, it didn't start with no acceleration because if it started with no acceleration, then it would just remain at rest, right? So we needed to have some acceleration to actually start the disk moving, and that would be an angular acceleration. So the angular acceleration wasn't 0 when it started, nor was it 0 as it continued to move because it continues to speed up. All right. Many times we'll talk about constant angular acceleration. It turns out that that's very common. All right. Just like constant translational acceleration is very common. In fact, systems that are driven by gravity are going to have constant, at least some systems are going to have constant translational acceleration and constant angular acceleration. All right. Pulleys we'll see. Okay. But we'll also see a variety of systems that don't have constant angular acceleration. Things that are tipping over. All right. Okay. But here's our first introduction to angular variables, okay? Not our first introduction to circular motion, right? Just a new way to think about circular motion, a way to describe the disk as a whole instead of just one point on the disk, all right? So, rigid body fixed axis rotation is rotation where the shape of the rotating object doesn't change. That's the rigid body part. That's going to be everything we talk about. And then the fixed axis is the idea that the point about which the object is rotating doesn't change while it's moving. All right? So the axis of rotation is always located at the same location of on the rotating body. So even if it was rotating, right? So it was rotating about that fixed point, and then that fixed point was translating like a rolling object, that would still be fixed axis rotation because the axis remains in the same location relative to the rest of the body. Okay? All right. Obviously, non-fixed axis or non-rigid body rotation is incredibly complicated and not something you can really solve by hand or would require computational power. Okay? All right, so these are our big assumptions that we're making. Now, let's discuss their two new vectors, the angular velocity vector and the angular acceleration vector. Okay? So the angular acceleration vector, omega as a vector, is delta theta over delta t. All right? And this, of course, is average. We'll talk about the derivative definition on the next page. All right, but this would be the average angular velocity vector. It is the rate of change of angular displacement. Okay, so it's radians per second, because the displacement is measured in radians. Okay, 2 pi radians make a full revolution. Okay, the direction of omega is found with your right hand. Okay, all right. So this is the first time we've seen something called the right hand rule. It's not going to be that big of a deal in this chapter, in chapter 10, but it's going to set us up to be a big deal in chapter 11, because chapter 11 is where we take rotational motion and we really start dealing with it in terms of the cross product relationship between some of these angular vectors. So chapter 11 is where we actually see the cross product, an idea we introduced in the first chapter, actually applied to a physical concept. We'll apply it to torque, we'll apply it to angular momentum. Okay, so we'll see it then, and then we'll be using the right hand rule quite a bit. In this chapter, in chapter 10, it's more of a side note, but it's good to be thinking about it ahead of time. Okay? All right, and then alpha as a vector is the change in the angular velocity vector over the change in time. Okay, so it's the rate of change of angular velocity. and the direction of alpha is along the same axis as omega and is parallel if omega is increasing. Okay? So check it out. Okay? Anti-parallel if omega is decreasing. So here we have our rotating a disk in. We can think of it as the same rotating disk that we drew up here. And this is maybe looking straight down on the rotating disk. And this is looking from the side. This is a real 3D perspective here. Okay? And the reason it's a 3D perspective is so I can clearly show that this line right here, the black line that was pre-printed on the page, is the axis of rotation. Okay? If this was like a physical wheel, it would be the axle. Okay? And so that axis of rotation is where these new angular vectors point. And that's interesting. And something that you may be kind of wondering about, well, why do they point along the axis of rotation? Because first of all, that means that they're actually perpendicular or orthogonal, so another term for perpendicular, to the plane of rotation, right? Because the plane of rotation is here. It's the disk, right? That's the part that's actually rotating, right? If we had, X, Y, and Z, okay, X, Y, and Z, then the plane of rotation would be the XZ plane, see? And the Y would be perpendicular to that plane of rotation. That's the idea. So it's kind of odd that the vectors that describe the rotation are perpendicular to the rotation itself. But after all, they are parallel to the axis of rotation. And they kind of need to be, because they describe the object as a whole. So it wouldn't make sense to draw them at a particular point on the object, because then they're a translational vector. And it wouldn't make sense to draw them, parallel to the plane of rotation, because which way would they point? Would they point off this way or this way? There'd be no meaning. So the only really unique direct direction that they can point that describes the rotation of the plane as a whole, whether it's a disk or a cylinder, whatever it may be, or even a sphere, it has to be perpendicular to the plane of rotation. It has to be along the axis of rotation. All right? And the right-hand rule is done like this. Take your right hand and curl your fingers. And we talked about this a bit with the cross product, right? But we talked more about thinking about using the right-hand rule to see cross products, because there's kind of two versions of the right-hand rule. And the one I'm talking about right now would be the simple version of the right-hand rule, where you simply curl your fingers and use your thumb. You don't have to worry about which two fingers which one is the A vector, which is the B vector, which one's first, and which one represents the cross of those two vectors. Okay, we'll deal with that later. For now, just curl your fingers in the direction of the green arrows. Okay, make sure to use your right hand. And when you curl your fingers in the direction of the green arrows, notice that your thumb naturally points in the direction of omega. It has to. Okay, so that tells you if the system is rotating in the counterclockwise direction, then omega must point up. All right? On the other hand, if it was rotating in the clockwise direction, then omega would point anti-parallel to the omega shown. It would point down. All right? And look at this alpha. Alpha points along the same axis of rotation. Okay? You see, I intended to draw it that way. It probably looks a little angled. But it points anti-parallel. That means that this particular example of angular acceleration would be slowing the disk down. If, on the other hand, angular acceleration pointed this way, then it would be speeding the disk up. Okay? All right. So those are our angular acceleration vectors and how we see them with the right-hand rule and where they point as a general vector, right? Describing the object as a whole. All right. Let's look at our key formulas. Okay. Let's get them. So first one here is the definition of radians, really. Okay? It's angular displacement in radians, which is arc length in meters divided by radius in meters. Okay? And this idea that this is how you define radians as arc length over the radius is really the reason we use it instead of degrees, because having this relationship is incredibly useful. Right? Arc length, so some segment of the circumference, and then divided by the radius. That's what radians are. Okay? Good. Excellent. All of the kinematics and dynamics, all the thetas are going to be in radians. Remember that. Okay? Another quick definition, a revolution is 360 degrees, which is also equal to 2 pi radians. When I write rad, that stands for radians. Okay? Not to be confused with radial, okay? Because radial is a subscript on a translational acceleration term. Radians is kind of like a unit, and it's the unit of displacement. Okay? I say kind of like a unit because it's dimensionless, but it is still, it's a counting tool. Okay? All right. Here we have the definition of angular velocity. Okay, here's the limit definition, and here is the derivative, right? So angular velocity, omega, right? Don't worry about the vector here, just its magnitude, is d theta over dt, right? So it's radians per second, because theta is measured in radians. It is the angular displacement, okay? And here we have angular acceleration. It is the derivative, the first time derivative of angular velocity, represented by the Greek letter omega, all right? So it's d omega over dt, okay? You could also write it as d dt over theta, or of theta, right? So, squared. It's the second time derivative of displacement, okay? So same exact idea of translational kinematics, but here they are rotational, right? So instead of x's and y's, it's all thetas and omegas and alphas, okay? All right, so this is the new stuff, and now let's relate the new stuff back to the old stuff. In other words, let's relate these new angular quantities, all right, these angular kinematic quantities, to the translational quantities of a particular point on a rotating body, okay? And again, remember, these ones describe the rotating body as a whole. Now, I keep saying that, but that's an important distinction, okay? So here we have the velocity of a point on a rotating object. R is the radius, okay? That need not be the actual total radius of the object, but that is the radius to the point. That is the distance of the point from the axis of rotation, okay? And omega is the angular velocity of the object as a whole, all right? So v equals r omega. Notice the units work out because it's meters per second, and then meters for the radius, and then radians per second. Well, radians aren't a unit, so then we're just left with meters per second on both sides, okay? All right, so v equals r omega. Likewise, omega equals v over r. We'll use that a lot, okay? All right, now the two forms of translational acceleration. Because translational acceleration, there's one, right? But there's two components. And it's really useful to think about the two components, the tangential and radial components of translational acceleration, because then we can easily relate them to the angular terms. Okay? That's why there's such a good choice of axes. All right, so the tangential component of translational acceleration, represented as a sub t, which we've seen before, all right? But now we're going to define that as r times alpha. Okay, this is a new way of thinking about tangential acceleration. It is the radius times the angular acceleration. Okay, again, note that the units work out, and this makes sense because alpha represents how fast the disk is speeding up, right, or slowing down, and so that's going to affect the tangential component of translational acceleration. Okay, well, the radial component of translational acceleration, a radial, or just AR, is v squared over r. We've certainly seen that before. And that means, since v is r omega, we can substitute in v for r omega, cancel out one of the r's, and find that the radial component of translational acceleration is omega squared r. All right, that's pretty interesting. So that's telling us that the radial component of translational acceleration grows with the square of angular velocity. Okay, so if your angular velocity is growing, then your radial acceleration is growing very quickly, right? Because it's a squared relationship. And also note that radial acceleration and centripetal acceleration are absolutely synonyms. And that's why, that v squared over r, that's what we always called centripetal acceleration. But even back when we first introduced it, I made a big deal of pointing out that those terms are interchangeable. Centripetal, radial, they mean the same thing. They both mean pointing towards the center of the circle. Okay? All right? Total translational acceleration, found because these are axes that are perpendicular to each other, so they form a right triangle. So we can just use the Pythagorean theorem to find the total translational acceleration from the two components. All right? So what these equations do, what these four equations do, is they relate translation to rotation. And they're actually quite useful. They're going to come out quite a bit. In this set of notes and future sets of notes, we'll have to keep kind of going back to them. Because any time we want to go from describing a rotating object as a whole to considering one point on that rotating object, maybe the tip of a rod or the bottom of a physical pendulum or the perimeter of a spinning disk or the the equator of a rolling sphere, all these ideas. Well, we use one of these equations to relate rotational to translational. All right. Well, let's get to the actual practice. Let's do the examples. All right. So let's do it. Only two types. As this is a introductory section here, so it's heavier on the ideas and lighter on the actual difficult problem solving. Okay, so type 1, problems that involve constant angular velocity and zero angular acceleration that highlight the relationship between angular and translational quantities. All right, so again, basically just going to be using this relationship. And then type 2, problems that involve non-constant angular acceleration that highlight the relationship between angular and translational quantities. This includes pendulums, okay? And pendulums will come up quite a bit. That's why I mentioned them. All right, so example 1. A rigid disk of 1.5 meters, that would be radius 1.5 meters, spins about a fixed axis with angular velocity, omega equals 3.91 radians per second. Okay, this is how we'd specify an angular velocity. What is the angular position as a function of time for the disk? How many revolutions does the disk make after 1 minute? What is the angular acceleration as a function of time for this disk? What is the translational velocity and acceleration as a function of time for a point along the outer edge of the disk? Okay, so let's use our definition of average angular velocity, which is going to be delta theta over delta t. All right, and in this case, because omega is a constant, the average is also the instantaneous. All right, and so it's just going to be the displacement over the time. Right, that's great when it's constant. All right, so that means that my displacement is just going to be my angular velocity times time. All right, or 3.91 times t. All right, and that's a function. Okay, it's a linear function because essentially I had omega as a function of time was a constant, which meant that theta as a function of time is linear, as we see. Okay, we're used to these types of relationships. We saw the same thing in translational acceleration, right, or translational kinematics. All right, and B, now we're asked to ask a particular question: how many revolutions after 1 minute? All right, well, I'll just plug in 60 seconds for my value of t. That's going to give me 235 radians, and I know that 2 pi radians is a revolution, so I can convert the 235 radians to revolutions by just dividing it by 2 pi, which is about 6, right? And so then I get a displacement, all right? So it's still an angular displacement, so I'd still represent it by theta, but I'd clearly denote it as revolutions, and it's 37.3 revolutions. So 37.3 turns. It didn't say complete turns, we don't have to round, just 37 and about a third turns, all right? Revolutions. Okay? And now, this should say C. So part C, what is the angular acceleration as a function of time for this disk? Okay? All right. Well, omega is a constant, which means that angular acceleration has got to be 0, right? We saw this in translation. If I have constant velocity, then I don't have an acceleration. That's the whole idea, right? So since I have constant angular velocity, I have 0 angular acceleration. Excellent. Okay? All right. So then, part D, so I think I labeled, I'm still kind of mixed up, right? This should be a C and a D. I don't know why I did that. But anyway, so here I asked, what is the translational velocity, okay, and acceleration as a function of time for a point along the outer edge? Okay, so V equals R omega. All right, so here's an interesting fact. And since omega is a constant, that means V is going to be a constant. Okay, and it also means that A is going to be a constant. So that's really weird, right? I mean, it's weird to think that we can have a constant velocity system that has a constant acceleration. But that's because we're talking about different kinds of velocity and acceleration. We have a constant, here it is, constant angular velocity system, which means that it has a constant translational acceleration. Okay? And that is really something you want to wrap your mind around. That constant angular velocity does not mean 0 translational acceleration. In fact, it means constant translational acceleration. All right? And actually, the other side of that, and I'll point this out in future examples in future lectures, constant angular acceleration means non-constant, changing translational acceleration. It's like there's an extra level of change that's built in to the kinematics here. Rotational systems, they're more complex, and a constant rotation there's more to take account of. Okay? All right? But we can calculate it with this concept out of the way. We can then say that the translational velocity is just r times omega, so it's just 5.87. All right? And I was asked for a function, right? So what is the translational velocity acceleration as a function of time? Well, it's a constant, so it's not really a function, it's just a value. All right? And then if I want to find the radial acceleration, it's just v squared over r. And so then I just take that constant value divided by the radius, and I find that radial acceleration, which is 22.9 meters per second. Then you might be like, wait, but it didn't ask for radial acceleration, it asked for translational acceleration. Well, what would the tangential component of translational acceleration be? Well, a tan just equals alpha r, and alpha 0. So there is no tangential component of translational acceleration, which means the entire translational acceleration is the radial component. So that's it. Okay? So there's our answer. Right? And again, they're not functions, they're just constants. Okay. All right, let's do another one. Let's do a concept question. Okay? So the figure shows plots of angular displacement, theta, for 3 cases of a rotating disk. Okay? So these are parabolas. All right? At least, they look like parabolas. We're not sure, right? But, they at least, definitely have, as far as we can tell, they're parabolas. They're definitely not linear, right? And so we should be used to this idea of kinematics, right? And this is displacement, right? So this would be like x versus t, but now it's theta versus t. If I see a parabola in x versus t, that tells me that I must have linear velocity and constant acceleration, okay? But these are different parabolas, right? They have different values, some are curved up and some are curved down. So but we should be able to make sense of it, to make the same graphical, kind of connections that we've made before about the meaning of a tangent line for kinematics and so on. All right. So A, at what value of time does each disk change direction? Okay. Well, changing direction means you have a momentary velocity of 0. A momentary velocity of 0 is a horizontal tangent line. So we just need to look for all the points of horizontal tangent lines. Okay. All right, so -2, 0, and 2, right? So -2 right there, 0 for the purple one, and then 2 for the blue one, right? And I color-coded them. All right? At what value of time is the angular velocity omega 0? Okay, well, the angular velocity would be 0 when the tangent line is 0 at the point where the direction changes. So it's the same thing. Okay, good. For each case, is the angular acceleration 0, constant, or non-constant? Okay, not 0 because theta is not linear, right? Now, if one of these lines was linear, then that would mean constant angular velocity and 0 angular acceleration, but none of them are. They all look like they're parabolas. They're at least some polynomial higher than 1, so that means they must all be non-constant, all right? Okay, or at least must be all non-zero, and they're probably all constant, because they do all look like parabolas. Okay, so probably constant, definitely not 0. Okay? And for each case, is the angular acceleration positive or negative? Well, that's the curvature, right? So if the curvature is positive, which means it curves up, like it would hold, if it was a bowl, it'd hold water, that means that the angular acceleration is positive, all right? That's how, the idea is when you have a function and its second derivative is its curvature, and remember that alpha is the second derivative of theta, there we have it, right? The sign of the angular acceleration is the curvature of theta, all right? So positive for the green one, negative for the purple one, and positive again for the blue. Okay? All right, now let's do another quantitative example. What is the angular velocity of a second hand of a watch? What is the translational velocity and acceleration of the tip of the second hand if it is 1.6 centimeters long? Okay? All right, so we're going to use omega equals theta over t, like we did in example 1. All right, so it's just 2 pi radians over 60 seconds, because that's a revolution. It makes a revolution every 60 seconds. That's what a second hand does, which means it has the angular velocity of 0.105 radians per second. Not particularly fast. Second hands aren't particularly fast. Okay? All right. Then if we want to find the translational velocity of its tip, well, that's why we need to have a particular length, because otherwise it wouldn't make sense. And it's omega times r. So we just take that value and multiply it by the radius, converted the meters here. And so then we get a value of 1.68 times 10 to the negative 3 meters per second, or 1.68 millimeters per second. That's how fast it's actually moving, right, in a translational sense. All right, looks good. All right, another one. A person is on a spinning, I forgot I asked for the angular, or the translational acceleration as well. Okay, so the translational acceleration is v squared over r, and so we just square that and divide it by the radius, and then we get a very small value. Because essentially this is the centripetal acceleration, and we shouldn't expect the centripetal acceleration of the second hand to be that big, considering how slowly it's moving. So in other words, there's not much tension on the second hand due to its rotation. That makes sense, because it's not like a high performance system. It's just like slowly moving along, right? So very, very small translational acceleration, and we could then turn this into a tension if we knew its mass. Okay, all right, but that would be kind of assuming all the mass is the end of the hand, which isn't true. So we would be better off finding the torque at the pivot point, but we'll be talking about torque later on. More on that later. Okay, so a person is on a spinning amusement ride with a radius of 9.5 meters. In a period of 5 seconds, the ride's angular velocity changes from 2.2 radians per second to 3.6 radians per second, from omega 1 to omega 2. All right, and at the end of that time, the ride's instantaneous angular acceleration is 1.1 radians per second squared. What is the ride's angular acceleration during the specified time interval? Is the angular acceleration constant? And what is the person's translational acceleration magnitude and angle measured from the radial direction at the end of the 5-second period? Okay? All right, so first of all, what is the average angular acceleration during the specified time interval? All right, well, that's literally just going to be delta theta over delta t. Okay, just the definition of average angular acceleration. Right, and again, you can imagine doing this all of translation, right? Just be a average equals delta v over delta t. See how everything is just, there's all parallels between all the terms we were used to in translation now with our new angular terms, okay? Because they are. They all have parallels, right? All our quantities. So then we get 0.28 radians per second squared, our average angular acceleration. All right? Now, is it constant? Well, no. Because look, the average is 0.28, and we were told the value at the end of that time period is 1.1, which is way bigger than 2.8. So clearly it's not staying constant, it's speeding up. Okay? Okay? So it's definitely not a constant angular acceleration. Okay. Now in part C, we want to consider this picture because we're asked for an angle relative to the radial direction. Right? So here is the radial acceleration, here is this is the radial translational acceleration, here's the net translational acceleration, and here's the tangential translational acceleration. Okay? So radial translational, net translational, tangential translational. Okay? And these are both components of the net translational acceleration. All right? So let's do it. So the radial component of translational acceleration is omega squared times r. All right, since we're dealing with the end of the 5-second period, we're going to use the 3.6 squared times our radius of 9.4 meters. And so we get about 120 meters per second squared, right? Not radians per second squared because we're not talking about angular acceleration here. All right, so then we want to do the same thing in the tangential. Tangential, we know that at the end of that period, that particular instant in time, right, because apparently it's changing, but at that particular instant in time, the angular acceleration is 1.1 multiplied by the radius, because again, this is the way we relate tangential translational acceleration to rotational acceleration or angular acceleration. It's a10 equals alpha times r. So in this case, 1.1 times 9.4 or 10. Wow, significantly smaller, right? So in other words, the centripetal or radial form of translational acceleration is way bigger than the tangential form. All right? And so then we're going to go ahead and find the overall magnitude of the translational acceleration using the Pythagorean theorem. And it ends up actually being 120 to 3 sig figs. All right? Actually, to 2 sig figs. There were actually, because I'm rounding the 2 because everything had 2 sig figs. Yeah, otherwise it would. I think it's like 122 or something. But it rounds down to 120. All right? And so then let's find the angle. And we're going to find the angle by just considering opposite over adjacent. So a tan over adjacent, which is AR. Right, so a tan over AR, take tangent inverse. So take tangent inverse of 10 over 120, and you get 4.9 degrees. Right? Notice I give this one in degrees. Right? I don't give it in radians because if I'm thinking about the angle between two vectors, I don't think of them in radians. I don't think, oh, that's like I don't know, pi over 12 radians or something. I think it's more intuitive to think of it in degrees. 5 degrees, you can quickly think, oh, okay, well, there's 90 degrees in a right angle. 5 degrees, that's small, right? So I will always still refer to angles between vectors or angles between like a slope, a slope in the horizontal or something in degrees. But at the same time, I'm going to do the kinematics, the displacements, in radians. So you got to go back and forth. Sometimes that even involves, right here, you'd have to make sure that your calculator is in degree mode. Sometimes, if we're doing other systems, you got to make sure your calculator is in radian mode. So you have to be aware of what angular unit is being used. Okay. Okay. On the other hand, you could report an angle like that in radians if you want. I would accept it. All right, another example. Okay, so this is our last 2 examples. These are our non-constant angular acceleration quantitative problems. Okay, so a rigid disk of radius 1.5 meters starts from rest and spins about a fixed axis with an angular velocity given as this function. What is the angular position as a function of time for the disk if we assume that the initial angular displacement is 0? Okay, well, how do we do that? Well, we integrate. Right? Because just like, we had x minus x naught equals the integral of v dt, now we have theta minus theta naught equals the integral of omega dt. Okay? Because, if If omega is the first derivative, then we should go backwards and be able to do antiderivatives. Okay, which is why we needed to know the initial condition so we wouldn't be stuck with a constant integration. All right, so then we just have, since we're told that theta naught is just 0, we have then that theta is our integral here, integrating from 0 to t, all right, of the function omega. This is a function of t, right? All right, then we're integrating with respect to t. All right, and then we're just going to do our rules of antiderivatives of polynomials. Our 16t squared becomes 16t squared over 2, or 16t becomes 16t squared over 2. Our 3.2t squared becomes 3.2 over 3t cubed. All right, obviously a negative there. And so that's it. This is going to be our function. And I rewrote the 3.2 over 3 as 1.07. Okay? And 16 over 2 obviously became 8. All right, units are radians. Right? There is a function. It ends up being a third order polynomial, which makes sense because it should be one order higher, and we had a second order polynomial with respect to t for omega. Okay, now we're going to go the other way. What is the angular acceleration as a function of time for the disk? Okay, well, angular acceleration is the derivative of omega, so we'll just take the derivative of this function, and then that, then the 16t just becomes 16, and the 3.2t squared becomes 6.4t. All right, units radians per second squared. Right, nice. And we got our two functions, and in fact, we have all three of the functions. Right? Everything we need to know about kinematics right there. It's a little bit of calculus. Okay, now interestingly, in part C, we're asked what is the translational acceleration as a function of time for a point along the outer edge of the disk. Okay, so then we'll have to use that the expression that has the square root in it, because that should be our total translational acceleration. And neither of the terms are going to be 0 because there's a non-zero angular acceleration. Or even if it was constant, we'd still have no 0 terms. So we're going to use this. Total translational acceleration is the square root of ar squared plus at squared. All right, and then we're going to rewrite ar as alpha r, make sure to square it, and then rewrite tangential acceleration as omega squared. Oh, I switched the order. If you please excuse that. But so the radial component is this one, and the tangential component is that one. All right, doesn't matter I switched the order because they're just added together, but I did switch the order. Okay, and then we'll just plug in the expressions. All right, so one thing I do is I factor out the r squared, because there's an r squared in both of these. So I factor out of the square root, and it just becomes r. That's where the 1.5 comes from, because we were told that the radius is 1.5 meters. All right, and then we'll just plug in our function for alpha right here. Remember to square it, and then we'll plug in our function for omega, the one that was actually given in the statement of the problem, the 16t minus 3.2t squared. And then the omega was squared within the definition of radial acceleration, and then we squared it again because we were, after all, using the Pythagorean theorem, which means that after we factored out the r, we're left with an omega to the fourth. Don't forget that. All right, raised to the fourth power. It's no joke. All right, and then we have units meters per second squared, because after all, it is a translational acceleration. All right, now, let's find a value of it. Let's use this big clunky function for something, because it really is, right? It's a pretty ugly function, right? But let's plug in a value of t. What value? Well, I don't give it to you. I ask you to find it. What is the translational acceleration of such a point when omega equals omega max? And again, remember, this is the translational acceleration of a point along the perimeter. If I asked for a point that was, say, halfway between the axis of rotation and the perimeter, instead of using 1.5, you would use 0.75, just half of 1.5. Okay? But again, we're going to plug in a particular value of time. But when is omega going to equal omega max? Well, omega equals omega max when alpha equals 0. Right? Again, just think tangent line. Okay? That's a horizontal tangent line. That's a local maximum. There's only going to be one local maximum because it's a parabola. And so then we just have to solve this function for t, which is as simple as subtracting 16 from both sides, dividing both sides by negative 6.4. So then t is just 16 divided by 6.4, or 2.5 seconds. Wonderful. All right? Then we're going to plug that 2.5 seconds into this expression here. Okay? That's all I do here. Plug it in. And amazingly, it gives us an integer, 600 meters per second squared. At that particular moment in time, that is the total translational acceleration of a point along the perimeter of our disk, right? Which is really fast, right? I guess it's a really fast disk of some sort. Maybe it's in some sort of high-tech machinery. All right, so let's do our last example, the pendulum. All right, so a pendulum is released from an angle, which is 56.5 degrees. A moment later, the pendulum is at an angle of 32.8 with the vertical, all right? And I guess that the one that's shown is a 32.8. We weren't shown the initial one. Okay, started up higher. At that moment of 32.8 degrees, what is the total translational acceleration of the pendulum bob, okay, which you've done before, and what angle does alpha make with the string? And then, what is the angular acceleration alpha? That's a new sort of question. And is alpha constant? And I forgot to put in the body of the problem. Apologize for that. But we do need to know the length of this pendulum. L has to be specified. M doesn't need to be, but L does have to be. And it's 1.5 meters. And I say L needs to be specified as long if we want numerical answers. Okay? Which we do. Okay? So this is what we're going to consider. A couple things. So first of all, we're going to need to use conservation of energy to find the translational velocity after the pendulum has swung from the initial displacement of 56.5 degrees measured with the vertical to 32.8 degrees measured with the vertical. All right. And if we're going to use conservation of energy, we need to relate those angles to a height. And so we're going to use this familiar expression based on this right triangle. Okay. I hope it's familiar. We've used this quite a bit every time we've worked with pendulums, especially when we use conservation of energy. And then the other idea here is that our external acceleration is going to be gravity. It's going to have components. Gravity is going to have a radial and tangential component. The radial component of gravity just creates tension, right? But the tangential component, it is actually going to be creating the motion. The net gravity is this one, or the total gravity. And then in terms of the components of acceleration, there's centripetal acceleration, which is entirely dictated by the velocity of the pendulum. And then there is a net translational acceleration, which is going to be a sum of the centripetal acceleration and the tangential component of gravity. And then the angle that's asked for in part A is this angle here, which is phi, because we're asked, what angle does the total translational acceleration make with the string? Well, that's phi. Okay. All right. So that's kind of what the picture's going to look like. What does the actual process of solving look like? Well, we'll use conservation of energy to go from E naught to E. So again, E naught started up somewhere here when the pendulum was up higher. So that would be the initial energy. And once it swung down this lower angle, that's point, or the final state. All right. And so initially it was at rest. So its energy was entirely gravitational potential energy. After it swung down, it has translational kinetic energy and gravitational potential energy. Now you might wonder, are there any other types of energy? I mean, we are talking about rotational systems here. Well, pretty soon we're going to see something called rotational kinetic energy. But it turns out that this particular type of pendulum doesn't have it. And I will show you why in a later lecture. But for now, just take it at face value. This is a complete description of the energy, even considering the fact that this is a rotating system. And it does have, a angular acceleration, because, we could treat it as one total rotating system, rotating clockwise about its pivot point. Okay, so just kind of a note there. If you wonder about, or if you've heard of rotational kinetic energy before, it isn't relevant to this problem. Okay, so carrying on. Well, that allows us to solve for v. Right, so that's going to be the velocity that we get with conservation of energy. This is the same velocity we get for something free falling, because remember that gravity is path independent, so it doesn't matter that it swung down, since there are no non-conservative forces in this system. All right, but anyway, there is our final velocity. Okay, and then what we're going to do is acknowledge that h naught and h are found with this, with the geometry that related L and theta. That's all I've done here. Substitute them in, and then I'm just going to apply. And then the reason I do this is because it cleans up really nicely. We're able to basically pull out the L. All right, now let's see. So we have 2g. I think I just forgot to write the L in there, but I do it on the next line. All right. So then we have. Anyway, so here we have 2.39 meters per second. Okay. Yeah. Anyway, so 2.39 meters per second is our velocity of the pendulum after it's swung down that much. Okay. And we see gravitational acceleration has both a radial and tangential translational components, but only the tangential component actually creates motion. Again, as I said, the radial component just creates tension. All right. And so then we'll find the net translational acceleration. We'll plug in our values. So the radial component of translational acceleration is just going to be v squared over L, because it's centripetal. All right. And then the tangential component of the net translational acceleration is just a component of gravity. It's this component of gravity, which is g sine theta. Okay. And so then we'll plug in the velocity that we found using conservation of energy. And then we'll just plug in gravity, plug in the angle that we were given, all right, the final angle. So really the only thing we needed to do ahead of time was find that velocity using conservation of energy. And then we find out that our net translational acceleration has a magnitude of 4.17 meters per second squared. That'd be the length of this vector here. All right. And then to find the angle, we're just going to take its tangent inverse of its two components, the tangential and radial component. The tangential is over here. And this tangential, if I drew it over here, is exactly g sine theta. Okay? And again, notice gr doesn't show up. Okay? That gr is not creating motion. Okay? All right? And so then our tangential, so then we're going to find phi. Phi is going to be tangent inverse of g sine theta over v squared over L. Okay? Plug in our values. And there we go. 54.3 degrees is this angle. Okay? Looks good. All right. And then we'll carry on and find alpha. Okay, so alpha is just going to be the tangential component of translational acceleration divided by L, which is just going to be g sine theta over L. Okay. All right. And it's 3.54 radians per second squared. And interestingly, once it's at the bottom of the swing, it actually wouldn't have a angular acceleration, because at that point, there would be no tangential component of gravity. At that moment, it'd be momentarily moving at constant velocity, just for that instant in time. Okay? And that definitely tells us that alpha is non-constant, because look, alpha is dependent on theta. All right? Which is a pretty complicated relationship. How would we actually, think about it? How would, for example, would we find alpha as a function of time? Well, we actually don't have the tools yet to do that. Okay? That requires solving a simple differential equation, and then it ends up being that it's sinusoidal. But for now, we can at least say that alpha is dependent on the angle theta, and it's definitely non-constant. Okay? Pendulums have non-constant angular acceleration, which means they have non-constant everything else. Because if you have non-constant angular acceleration, that means you have non-constant angular velocity, you have non-constant translational velocity, and you have non-constant translational acceleration, because both the components are going to be changing with time. Okay? And changing with angle, for that matter. But here we have it, right? How we think about the rotational kinematics, the rotational terms that relate to a pendulum, a system that we're going to keep coming back to. Okay. All right. Well, thank you so much for listening to this lecture. I hope this introduction to this new rotational material has been interesting and informative.